Hi there and welcome to this PowerCrest video on power factor correction basics. In this video I'll be looking at concepts such as what are VARS, some power flow conventions. I'll be looking at what is VAR compensation and why is it needed, power factor correction, and I'll finish off with an example. The example hopefully would help to consolidate and clarify all the principles and terminology discussed. What are VARs? In a power system, power is defined in terms of apparent power S, real power P, and reactive power Q. Right. The units are volt amperes for S, or we can have kVA, MVA, etc. For power, for real power, the units are watts, watts, kilowatts, megawatts, and for reactive power Q, the units are volt amperes reactive, right? And so you can have kVAR or MVAR, etc. as well. The relationship is defined by S is equal to P plus JQ. So P being the real part of the apparent power and Q the imaginary or the reactive part of the apparent power S. P, the real power, is the power required in the system to do useful or active work. For example, it'll be the power required to allow a motor to produce torque so as to rotate a shaft, or the power required to heat a heating element such as found in domestic kettles or heaters, etc. Right now, the reactive power is the power required to establish magnetic fields in machines such as transformers, motors, and generators. Also, it's the power required to charge cables and transmission lines, right? When you have charging current flowing, charging current required to charge a transmission line or a cable, well, that's when we have reactive power flowing. So you could actually say that reactive power is the power required in order to enable active work to be done. Okay, let's take a look at the phasor relationship between S, P, and Q. Right, so the phasor relationship, right, may in simple terms be expressed by this diagram. Right, where we have Q being the imaginary part, P the real, and S being the combination, the complex power, or the apparent power. Now, looking at the basics of power factor correction, right? Power factor correction falls under the reactive VAR compensation umbrella. And its power factor is one of the ways of compensating for VARs in the power system. So you may ask the question, what does compensating for VARs actually mean? Well, having VARs flow throughout the power system means that there's increased current flow in the power system due to the reactive current required. Right, if you have rotating machines, generators, motors, and you have transformer, which is really just a static machine, these require a certain amount of VARs to operate or function correctly. Because they require VARs means that they are going to draw reactive current from the source. And of course, if you have current flow, increased current flow means you're going to have increased voltage drop due to this current flow. And of course, current flow has associated with it losses in the system as well. Thus, compensating for the VAR flow means finding ways of reducing the VAR flow throughout the power system, as this will lead to reduced losses, reduced voltage drop, less current. Well, less current means more system capacity available for real power flow. So in this video, we will look at one commonly used technique to reduce VAR power flow in a power system, and that is power factor correction. Okay, so what is power factor? Well, by definition, power factor is the cosine of the angle between the current and voltage of the system. So here we have a voltage phasor being the reference, and we see that there's a current, and the current lags the voltage by this angle theta. Right, so the power factor is the cosine of this angle theta over here. Lagging power factor, well, current lags the voltage, but we can also have leading power factor, where the current leads the voltage. So the current phasor would be sitting in this position over here. With unity power factor, current is in phase with the voltage. Right, so suppose theta is equal to minus 30 degrees, then our power factor is the cos of minus 30, which is equal to 0.87 lagging. Okay, let's look at leading power factor. Here we have voltage as our reference, and here we can see the current is actually at an angle leading the voltage. Theta is positive, right? So here the current leads the voltage by 30 degrees. Then our power factor, which is our cos 30, is equal to 0.87, and of course we have a leading power factor. So an inductive system is characterized by a lagging power factor, whereas a capacitive system is characterized by a leading power factor. Now, let's look at true power factor quickly. Really, we need to actually be speaking about true power factor, which is the product of the displacement power factor and the distortion power factor. Right, distortion power factor comes into play when considering harmonics. Now, harmonics is beyond the scope of this video, so by power factor, we will be meaning displacement power factor for purposes of this video. Right, so true power factor, right, is really the power factor based on the RMS VNI. Displacement power factor, the one we'll be dealing with in this video, is really the power factor which considers the fundamental voltage and current. And as I've said, distortion power factor is that due to the harmonics on the system. Okay, at this point in time, there is some basic maths I'd like to review regarding complex power, power flow, etc. And this is the phasor diagram I'll be working with. So, to start off with, we know that our complex or apparent power is equal to real power P plus J times the imaginary power Q. And that is also our voltage times the complex conjugate of the current. Right, the underscore means that we are looking at phasor quantities. Right. So I can expand that to the magnitude of E times the magnitude of I times the cos of minus theta minus J times the magnitude of E, magnitude of I, sine of minus theta. And I can rewrite that all as VI cos theta plus J VI sine theta. I'll explain in a moment how I moved from this line over here to this line over here. First to note is that P is then this part over here, which is VI cos theta, and Q is the imaginary part over here, which is VI sine theta. So, how did I move from this line to this line? Well, first note that I is equal to I, or the magnitude of I, cos minus theta plus j times the magnitude of I sine of minus theta. And so the complex conjugate means that we just reverse the sign of the imaginary part. So plus becomes minus. Everything else remains the same. But then we also have that the cos of minus theta is equal to the cos of theta, and sine of minus theta is equal to minus the sine of theta. So what does this all add up to? Well, it tells us that the magnitude of the angle between the voltage and current equals the angle, or equals the magnitude of the angle between S and P. Now, something else also to note in this phasor diagram is lagging current. Lagging current leads to leading reactive power. Right? I'll repeat that because it's a pretty important concept. We'll be discussing it soon again. Lagging current, leading reactive power with respect to our real power, which is our reference in this case. Conversely, leading current will lead to, leading current will lead to lagging reactive power over here. So what is the purpose of this? Well, by lowering Q, that is compensating for the reactive power, whilst keeping P constant, then the angle theta and S decreases. But if theta decreases, then cos theta increases, i.e. the power factor improves. What this illustrates is that by lowering Q, by lowering the reactive power, that the power factor has been improved. Of course, if theta decreases, then the angle between V and I decreases as well. Okay, before we move on, I think it'll be pretty useful at this point in time to have a look at power flow conventions. Okay, so here we have a bus and a feeder. Let's have a power meter with the power meter connected to the feeder by means of a current transformer, and it gets its voltage supply from the bus via our voltage transformer. Okay, so now we can have forward power flow. In other words, power flow away from the bus into the feeder, right? That would be forward power flow. And with power flow, we are talking about real power flow, right? The kilowatts flowing in the system. With forward power flow also, we will be talking about exporting power. So when we export power, power flows from the bus into the system. On the other hand, you can have reverse power or importing power, where real power flow is from the system into the bus, like we have here. Of course, the power can either be forward or reverse, which means that it can be represented purely by a straight line, right? Sort of a one-dimensional representation. So, to represent all cases of real and reactive power flow, the line needs to be extended to a two-dimensional plane split into 4 quadrants. Okay, so let's start off by looking at first quadrant power flow, right? We see we have real power P on the horizontal axis, reactive power Q on the vertical axis, such as here, and then we have our complex or our apparent power being the complex combination of Q and P, right? What could give rise to this? Well, let's suppose we have a source and we have a load at the far end of some feeder. And let's suppose we have a power meter located at the source. We have positive power, which means that power flows from the source to the load. This arrow is indicative of real power flow, not reactive, real power flow. Okay. Then we've got positive Q. What does this mean? Well, Let's look. Positive Q means that Q leads P. That implies that the current must be lagging the voltage. If the voltage was at this point over here, the voltage was our reference, then the current would be lagging the voltage. So whenever current lags voltage, we have an inductive load. So our load reactance, the net load reactance is inductive. And of course, I want to again mention that the phasor diagrams in this video, none of them are really to scale. Right? They're merely there to represent and illustrate certain concepts. In reality, the real power would be typically much greater than the reactive power because the load power factor would be hopefully close to unity, somewhere between 0.9 and 1. Okay, next up I'd actually like to deal with quadrant 3, not quadrant 2, and you'll soon see why. Right, now notice that quadrant 3 is really just a mirror image of quadrant 1 over here, right? Where in quadrant 1 we had power flow in the positive direction. Here we have it in the reverse direction, right, on the horizontal axis. In quadrant 1 we had reactive power flow, where the reactive power flow was in this positive direction. Now it's in the negative direction over here. So what does this mean? Well, it could mean, for example, that I have my power meter sitting at the load end over here, and it's been wired up so that forward real power flow is in this direction from our load to the source. Right, that would be forward real power flow. But because power is negative, that means the actual power flow, the kilowatts flow, is from the source into the load. Power is negative. Right. What does Q being negative mean? Well, it doesn't have anything to do with this sign over here. This sign is indicative of real power flow. Q negative, how do we interpret this? Well, a simple way I tend to look at it is Q negative over here means that Q is leading P. And I said earlier, when my reactive power leads the real power, then we must have inductive current, which means that I have an inductive load in the reverse direction, right, as you can see over here. Okay, in our next instance, which is the second quadrant power flow, we have the real power being in the same direction as the third quadrant, right? The difference is here that our reactive power flow has changed sign. Instead of being negative, it's now being positive. So what does this mean? Well, again, suppose our power meter is situated at the load end and it's wired up to be looking back towards the source. Negative power flow means that our power must be flowing from the source into the load. However, Q is positive in this instance. Now how do we interpret that? Well, in the previous situation, in the previous case when we had third quadrant power flow, Q was negative, and we said since Q was in this direction over here, it was leading P, which means that we had lagging current. Current lags the voltage, inductive load. So if Q is in the opposite direction this time, where Q now lags P, that means the current must be leading the voltage. Current leading voltage means I have a net capacitive reactive load. So my load is minus Jx, which means my load reactance is capacitive. Okay, let's look at our fourth situation, where we have fourth quadrant power flow. Okay, here we have P again being positive, but Q is negative. Okay, what kind of situation could give rise to that? Well, let's suppose again our meter is located at the source, load at the opposite end. Positive power flow means power flows from the source to the load. What does Q negative mean? Well, as we can see from this phasor diagram, Q is negative, which means that Q lags P, right? And we said that when Q lags P means that the current is leading the voltage. Current leading voltage implies capacitive reactance, capacitive current. And so my load would have a net capacitive reactance, right? So in this situation, I'm feeding a capacitive load, as well as a resistive load. So my complex load has a resistive and a capacitive component. Well, so let's look at an example. This should actually help to consolidate everything we've been discussing so far. And hopefully the example will make everything clearer, if there maybe are some things that have not been too clear up to this point. Okay, so let's go. Let's suppose we have a source over here, source connected to bus A. Then we have feeder 1, bus B at the end of feeder 1. We have feeder 2, bus C, the end of feeder 2. And connected to bus C, we have this motor load M1. Now, just on the aside, right, I've done this example using the Power Tools for Windows software, right, or PTW for short. It's an analysis tool, an engineering analysis tool from SKM. Okay, I've done a load flow study, and these are my load flow results, right? The source needs to generate 158.8 kVAR, right? So I can see over there 158.8 kVAR is which my source needs to generate, right? And I have 318.75 amps required. On the other end, I have my load, which I have where I have a 200 kilowatt motor. The power factor of the motor is 0.8, and you can see that's where my current's gone. So there's no other load on the system, so all the load over here, all the power generated over here is needed to supply the load. I have some voltage drop across my feeders. Okay, so we have seen that we have a source supplying a load, and across the cables we have a voltage drop of about 0.8 over here for cable 1, feeder 1, and another voltage drop of 0.8 for feeder 2. We see that the voltage at the source, the load flow voltage, is 479.41, which drops to 471.7 at the load bus. So if our cosine theta is equal to 0.8, right, if our power factor is 0.8, then the angle theta must be the arc cosine of 0.8, which is 37 degrees. So let's look on our phasor diagram. We have power, which is 211.75. We have reactive power, which is 158.8. And then we have our total power, the apparent power, at an angle of 37 degrees. So this is our starting point. This is what we have initially without any compensation on our system. Now, let's say we want to improve our power factor to 0.95, right? So cosine theta would have to be 0.95, which means theta would equal the arc cosine of 0.95, which is equal to 18 degrees. And if I do our calculations, we'll see that the new reactive power, the new Q value is 211.75 times the tan of 18, right? 211 being our real power, which is a constant, times the tan of 18. So our new Q is 68.8 kVAR, right? So we want to end up at 68.8, which means the difference, right, is 158 minus 68, which is 90 kVAR, and that is the size of the bank. So we see, just to recap, the size of the bank is what we started off with, what we want to end up with, and the difference between them. That's the size of the bank. I started at an angle of 37 degrees. I end up with an angle of 18 degrees, and you can see an appreciable reduction in the reactive power. Of course, the drawing is not to scale. So let's look at what's happened here. We've started off with the load flow initially over here. This is our initial load flow situation. We have a volts drop across all three buses. We have a power factor of the load of 0.8, power factor of the source of 0.8 as well. The single line at the bottom is the one where we've introduced our capacitor bank. Look what's happened at the source. We've gone from 0.8 power factor to 0.95. Our current has dropped from 318 to 267. The reactive power has dropped from 158 to 70.44. The real power is still more or less constant, 211, 210. Total power has dropped from 264 till 222. In other words, the introduction of the capacitor bank over here has freed up quite some capacity at our source. It's also decreased the amount of current that needs to be transmitted, the power that needs to be transmitted. It has reduced the current that needs to flow across our system, and of course less current means less volts drop. So where before 479, I ended up with 471. My volts drop is now only down to 473. So I've improved my voltage profile across the system. Well, I've also improved the losses because of less current flow. And you can see that the motor still gets the required load. The motor load is pretty much the same as before. The difference is that due to the capacitor bank. So the capacitor bank has made an appreciable difference by lifting our power factor, reducing the current flow throughout the system, improving the voltage profile, and also reducing the losses of our system. Okay, what I'd like to do is actually look into the action of the capacitor bank in a bit more detail. I'd like to start off by saying that the capacitor bank is not a source of VARS. Indeed, this bank over here, right, it does not supply the motor with VARS because the bank itself is not a source or sink of electrical energy. Well, in reality, the capacitor bank draws leading current from the source. The motor draws lagging current as well as real current, of course. They oppose each other, so the net current which the system needs to supply is reduced. You can see my motor requires 190 amps, but that's 190 amps reactive current, right? The capacitor 107 amps of reactive current. This would be lagging current, this would be leading current. So what flows from the system is the difference between the two, which is 83 amps. So you can see the reactive current, or the reactive component from the source, is 267 times the sine of 18, which is our 83 amps. So that is how a capacitor bank sort of compensates for the VAR flow. It opposes the inductive VARs flowing through the system because the capacitor bank draws capacitor VARs or leading VARs. And of course those two have a cancellation effect. And so our overall effect is to reduce the reactive power flow in the system. So to recap again, the benefits of having introduced the capacitor bank. Well, we have system capacity freed up, right? We only need 267 amps now to feed the exact same load as before. Previously, we needed 380 amps, so we have a saving of 51 amps. And of course, less current flow implies less system losses. And less current flow also means less volts drop, which improves the voltage regulation. Okay, so a word of caution. Right, as is obvious by the heading. It is highly recommended that a harmonic study be conducted prior to the installation of any capbank. Well, this is to ensure that the system harmonic profile is not exacerbated by the introduction of the capbank, and if so, mitigation measures may need to be taken. Right, harmonics and resonance. Right, resonance conditions could lead to harmonics, certain harmonic orders being present on the system. Right, these are bad news in general for the power system, including the capbank. So please be aware of these. Now, location, location, location. What is the ideal location? Where should I put the capacitor bank? Now, previously, we had the capacitor bank at bus C, close to the load. Now, what if I decided to put my capacitor bank over here at bus B? Well, let's look at the results. If you see, in the first instance, the current through feeder 2 is the current through feeder 1, which is 267.435 amps. However, in the second instance, because the capacitor bank is upstream of feeder 2 now carries the total load current of the motor as before, which is 318 amps. So, feeder 2 unfortunately has missed out on the benefits of the capacitor bank purely because the bank has shifted from bus C to bus B. Notice also the voltage at bus C is now 473. Well, the voltage initially at bus C is 473.55. Now it's 472, so there's a bit of a volts drop, right? So the bus C has also missed out on an improved voltage profile because of the capacitor bank. The power factor at bus C initially is 0.95, now it's dropped to 0.8. Why? Because the capacitor bank has moved upstream. So in general, the upstream network, right, is what enjoys the benefits of the capacitor bank. So poor feeder 2 has lost out. So it is recommended that the capacitor bank, where possible, right, be placed as close as possible to the load, so that as much as possible of the upstream network enjoys the benefits of having the capacitor bank in the system. Okay, so to recap, the capacitor bank to be located as close as possible to the inductive load. Well, I hope you've enjoyed this PowerCrest presentation. Please do share, like, and subscribe to my PowerCrest channel. And please feel free to leave a comment as well. You're also very welcome to visit my website at www.powercrest.net. Thank you, and till next time.